Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this lecture, we kick off I think maybe I've got 3 or 4 lectures that talk very specifically about programming in assembly language. And this first lecture, we're going to talk about the aspects of assembly language that deal with initializing and working with data memory. And then we're going to proceed to look at calculation-based assembly language programming, how to do mathematical operations, bitwise, logical operations. Then we're going to talk about implementing conditionals and loops. And then finally, we're going to talk about implementing function calls. And so to start off with, one question is why assembly language? And there's some debate, I guess, as to why people would want to learn assembly language. So very few of you are going to be most likely programming assembly language in your job. High-level languages are ubiquitous now. Compilers are quite good. You can program in a high-level language and get very good performance. So why would we want to look at assembly language programming? Well, hopefully, and you've seen this already if you've been watching all of these lectures in sequence, hopefully by now you understand that understanding assembly language and machine language commands is an essential part of understanding how microarchitectures are designed. And so the way that I've structured this course is, all the lectures up until now have started at a very low level, and we've basically built a little simple computer. We've basically built a microarchitecture that can do calculations, conditionals, and loading and storing from data memory. So it's impossible to understand how microarchitectures are designed without also understanding the very sort of simple assembly language, machine language instructions that run on those microarchitectures. And really, this course is all about understanding how computers are built, right? So that's the first reason. You can't understand how a computer is built if you don't understand assembly language. As we've seen, the microarchitecture hardware and a computer's instruction set are directly linked. So we had certain instructions, certain machine language instructions that we wanted to execute, and we built digital logic structures to execute those instructions. And so you can imagine when a company like ARM or Intel are designing a brand new processor, you are basically simultaneously developing the machine language instruction set and the hardware that runs those machine language instructions. If you are involved in toolchain development, so for example, if you're developing a compiler, you have to understand machine language, because the whole point of a compiler, as we've seen, is to take a high-level language like C or Python and translate it down into machine language and assembly language instructions. And finally, and this is where people will sometimes debate this point, but viewing a program at the assembly language level offers some insight into the speed of how quickly a program can run. There was a time when people would say that humans were always better at writing assembly language than compilers. And so, universally, a human could write a more efficient assembly language program than a compiler could generate. That's arguably no longer true. Compilers, particularly if you turn on a high level of optimization on the compilers, are pretty good at generating efficient assembly language instructions. But if you have been looking at the AVR instruction set manual, you'll notice at the end of each description of each assembly language command, it tells you exactly how many clock cycles it takes to execute that command. And so if you are working on some very performance critical embedded design, or if you want to use the simplest possible, slowest possible processor in order to save energy and prolong battery life, and you need to understand exactly how long it's going to take to do a calculation, really the only way to know for sure is to take a look at the assembly language commands that make up your little section of code and go to the instruction set manual and add up the number of clock cycles your computation is going to take. Also, I will, at this point out that it's not really, an either or choice between a high level language and assembly language programming. The microchip development environment, for example, that goes with the AVR processor, does allow you to write what's known as inline assembly code, where you can program in a high level language like C, but if there's a very performance critical chunk of your code, you can actually sort of embed your own custom assembly language code into that section of your program. We're not going to be doing that in these lectures. I'm just going to be writing total overall assembly language, complete assembly language programs from scratch. But just be aware that that is a capability that most development environments do offer. So in these lectures, I'm going to be switching back and forth between slides and the microchip MPLAB-X development environment. And so the chip that I've chosen for, to focus on in this class for our hands-on exercises is the AVR 128 DB28. And as we learn about assembly language, I'm basically going to use the AVR simulation capabilities of the MPLAB-X environment to run our assembly language code and to see how our assembly language would change the registers and the data memory on this particular AVR chip. We're not going to run on actual hardware, but you will be working on the actual hardware in the hands-on environments. And so I'll be switching back and forth between our development environment. All of the commands, of course, if we're focusing on this chip, the assembly language commands that we're going to be learning about are the AVR, come from the AVR instruction set manual. And I'm not going to have a chance to sort of go over all the commands in the manual. There are a bunch of them. But use that as a reference. So whenever I use a command in the lectures, you can look up that command in the AVR instruction set manual and you see a lot more detail there. So that's a handy reference. And so now let's switch over to the development environment and get ourselves set up to start talking about AVR memory. Okay, so if you fire up the MPLAB-X environment, this is what you're going to see. And I'm not going to discuss how to install MPLAB-X. I did post a document on the course website talking about how to install and install both the development environment and the compiler. So if you haven't already done that, please pause the video and go ahead and do that. If you're not part of the class, you're just sort of watching these videos from home, the installation of MPLAB-X is pretty self-explanatory if you go onto Microchip's website. And you should be able to install it on Linux, a Mac, or on a Windows computer. And so what I'm going to do, the first thing I'm going to do is I'm going to create a project in MPLAB that we're going to use to write, that we're going to use to test our assembly language. And so you click on the new project button, Microchip Embedded Standalone Project. You can just click Next. And then it's going to ask for our device. So we're going to choose the AVR 128 DB28. We're going to select the simulator. If you already have some experience doing hands-on programming with the MPLAB-X environment, you'll notice that if you've got the PickKit programmer plugged into your computer, you'll see that here as well. But we don't want to work with the PickKit programmer for this part of the course. We just want to use the simulator. So you click on Next, you select the XC8 compiler toolchain, and video lecture example. And I'm just going to call this project video lecture example assembly language. Set it as the main project so you can keep everything else here. You can keep all the defaults, then you go finish. It'll open up the project in the project screen here. We need to create an assembly language file. So if you go under source files, you click on new, assembly file.s. Now, it's going to take me a few tries to do this because for whatever reason, I've got I've got an Apple mouse and it doesn't love my Apple mouse. I think let's try that. No. Oh, yes, indeed. All right, there we go. And so I'll just call this lecture example. And then it automatically calls lecture example.s. There's also an option to create an assembly language file with the .asm suffix, but choose .s because that's what the XC8 compiler expects. Go finish. And this is it. It's a blank file. Now, I usually minimize my project window here, get rid of the start page, and there's going to be a few useful windows that we're going to be looking at in the debugger that will allow us to look at data memory and stuff like that. But I'll show you how to open those up as we progress in the lecture. So if you recall from our discussion of high-level languages, tool chains, and compilers, basically a high-level language file, like a C file, is converted from C to assembly language by the compiler, and then the assembler converts the assembly language command the assembly language file from assembly into an object file. And an object file is basically a binary file that consists of the actual binary machine language instructions that run on our microarchitecture. Now, if you an assembly language file is the assembly language file that's used to generate an object file is divided into a couple of sections. The first section is called the text segment. And the text segment is basically where we do our programming. So the text segment contains all of our assembly language instructions. And these assembly language instructions basically get mapped one-to-one to machine language instructions by the assembler. We also, as we're going to see, have something called a data segment in our assembly language file. And the data segment contains a series of commands that are used to initialize values in data memory. So before our program is up and running, there's a little bit of boot code that takes a look at the data segment of our assembly language file and uses the commands in there to initialize, to write certain values into data memory that are there waiting for our program when it starts to execute. And finally, object files have other information, relocation information, symbol tables, debugging information. This is useful for linking to other object files, for example, if we're calling library functions and things like that. However, we won't be getting into much of that in our discussion. So most of what we're going to be talking about will be one assembly language file that uses sort of AVR native assembly language, and it doesn't, we're not going to be calling like a bunch of library functions or anything like that. And so just to start off, let's switch back to the development environment and see how we create the data segment and the text segments of our assembly language file. Okay, so in our assembly language file, I'm going to indent with a tab, and I'm going to type in the command .data. And everything that follows the .data command is placed in the data segment of the assembly language file. And at the start of .data, I need to type in a special command. And it's basically, the purpose of this command is to allow us to initialize our data memory. So do copy data. So I said that we weren't going to be calling any library functions, but that's not exactly true. There are some sort of initialization little chunks of assembly language code that the compiler automatically brings in to help launch our program. And there is a little bit of code that is used to initialize data memory. So the data memory is actually initialized using assembly language commands that copy what we've written in our data segment into data memory. And those commands are in a function, if you like, called do copy data. And by using this .global directive, we just let the assembler know that there is a global function called doCopyData that exists, and if possible, link to it. And that allows the assembler to bring in that little bit of stub code to initialize data memory. So we're going to write some stuff in our data segment. I'm going to talk about that in a second. But below the data segment, we put in another directive called .text, and everything below there is the text segment. So this assembler allows C-style comments, so that's what I'm going to be using. So everything below .data is the data segment, and actually I'll put the comment above. Everything below .data is the data segment, and then everything below .text is the text segment. So I mentioned that this lecture is going to be all about the assembly language, aspects of AVR assembly language that deal with the memory on the AVR chip, and specifically data memory and instruction memory. So the concepts of data memory and instruction memory will be familiar to you because we had those two types of memory on the simple microarchitecture that we designed in the lectures leading up to this one. And if you look at the AVR datasheet for our microcontroller, you can see that the AVR microcontroller does in real life have separate memory spaces for instructions and for data memory. They use slightly different words. So if you look at the AVR datasheet, the datasheet will refer to two memory address spaces. They refer to code space, which is basically the instruction memory, and data space, which is basically the data memory. AVR flash is used, we think of AVR flash primarily as what we use to store our instruction memory, but you can also store some user data in the flash memory location. And so you'll see a portion of flash memory is actually mapped into the data space, into data memory space, and I'll show you a diagram that illustrates that in a second. The text segment of our assembly language program, so the commands in our text segment, are mapped into code space starting at address 0. So the very first assembly language command executed by our program maps into assembly language 0. The very first instruction, or the very first assembly language instruction that you write in your assembly language command won't be at address 0 because there is, as I said, there's a bit of boot code that gets copied in by the assembler to help the chip start up. But we'll be able to sort of view the locations both of what's happening at address 0 as well as the location in instruction memory where your first command is actually located. The data segment in our assembly language program doesn't start at 0, so the variables that we initialize in our data segment instead start at address 4000 hex. And that's basically starting at address 4000 is basically the location in SRAM data memory that we have to play with as programmers. So if you're writing in C, for example, and you use the dynamic memory commands like malloc and free, then you're going to be creating variables on what's known as the heap. And we're not going to be doing a lot of C programming in this class, so you're not going to be using malloc most likely in the lectures anyways. But if you do use dynamic memory inside your C program, all of those variables are placed in data memory starting at address 4000. So our data segment will initialize values at 4000, and then if we use the C dynamic memory functions, that also plays around with the area of memory starting at address 4000. Later on in our lectures, we're going to talk about something called the stack. And the stack is another area of dynamic memory that is allocated for use when we do function calls. And we're going to be talking all about those details. For now, I'll just mention that the stack starts at address 7FFF and grows down in memory space as you allocate, as you put more stuff on the stack. But don't worry too much about that detail. That's going to make a lot more sense as we get into our function call lecture. If you look in the AVR datasheet, you're going to see this picture. This is the picture of AVR data memory. You can see that we've got our code space and our data space, basically our instruction memory and our data memory. One thing that's a little bit confusing, you're going to see we're using 5 hex digits for our addressing here in code space. That's because for whatever reason, this diagram assumes byte level addressing, but the actual microarchitecture, the program counter within the AVR uses word level addressing. So it's possible to address our entire 128 kilobytes of memory using 16 bits rather than the 17 bits that are shown here. I'm not sure why they chose to do that in this diagram, but just that's what they did. If we look at our data memory address space over here, it's a lot busier. And you can see that it's not sort of the simple model of data memory that we had when we were talking about our microarchitecture. So we've got input-output memory. These are the special function registers that we write to and we read from when we're configuring the peripherals inside the AVR chip. So for example, if you're configuring a digital to analog converter or some digital I/O pins, you're going to be writing to registers that are mapped into this part of data memory. We've got some other special areas of data memory. I won't get into these in detail. You can reference those in the datasheet if you want. We've got some reserved address space, and then we've got 16 kilobytes of SRAM. You can think of this 16 kilobytes of SRAM as data memory as we were talking about it in our microarchitecture. So this is the location in data memory that we can basically play with as programmers when we write our assembly language. So I mentioned that if we initialize data memory in the data segment of our assembly language program, our variables will start at address 4000. If we create dynamic memory variables in our C program, those variables will be placed on the heap. And as we use more and more data memory with more and more variables, we will allocate space going upwards in data memory, going to higher addresses. And our stack memory is here at the other end of our data memory space, and it starts at address 7FFF and then grows in the other direction. It grows down in address space. But again, don't worry too much about the stack for now. Finally, the last little bit of data memory here we have is mapped flash memory. So it is possible for us to initialize the flash memory with useful data. So for example, if you wanted to write a sound file or something like that into data memory, you could or into instruction memory, you could do that, and then you could access it from the data memory address space. And so I just wanted to give you this overall big picture. As far as the areas of memory that we're going to be looking at in these lectures when we start to debug our assembly language code, we're going to be looking at code space. So we're going to be looking at, the addresses here. And this is a messy diagram now. And we're going to be looking at data memory, and we're going to be focusing on this area of data memory. As well, we're going to be looking at some of the registers from the register file. But those don't show up in data space or code space. They're in sort of their separate location in the register file. So anyways, keep this map in mind as we start to move through some of our assembly language examples and use the development environment to actually look at different areas of memory on the AVR chip. Okay, so let's go back to our development environment and start actually doing something with our assembly language program. So the first thing I want to do is I want to type in a series of commands into our data segment that will initialize our data memory with some values. And so in assembly language, you don't exactly have variable names, but you do have what basically sort of look like variable names that represent different addresses in memory. So I'm going to write var1 colon, and then I'm going to write the command .byte 0x11 0x22. So let's take a look at this line. So the string var1 is what's known as a label. And a label is basically an alias for a memory, a location in memory in an assembly language file. Now, in the data segment, we're initializing data memory, and we know that data memory starts at address 4000. So var1 is an alias for address 0x4000. After we provide a label, we then use a command to tell the assembler how we are going to initialize the data memory. The command I'm using here to start is the .byte command. And the .byte command basically tells the assembler that I want to initialize memory 1 byte at a time. I then follow the .byte command with a series of comma-separated values. Each one of these values represents a byte value that's written into data memory. And so I could just give it one value. I could give it a list of 3 or 4 values. In this case, I've given it 2 values. And so what that means is, so 0x11 is written to address 0x4000. And 0x22 is written right after it to address 4001. Okay, so what I would encourage you, so as I sort of type in these commands, I'm kind of doing these assembly language programs on the fly. I would encourage you to have, as you're listening to this video, to have the MP Lab development environment open and to be typing this into your development environment as I'm typing it into on my screen. Treat the development environment as how you're taking notes right now. I'm writing in notes in the comments here. I think you should do the same. Rather than just sort of taking a file that I provide and sort of going through it, just type it in now. Feel free to pause the video, type it in, think about what's going on, then start the video again. It slows down, but it's a more active learning style. So we're not restricted to just initializing memory byte by byte. There's also a word directive. So I can type in var2.word 0x33 0x44, and a word is 16 bits on the AVR instruction set. So just as to continue on the topic of labels as well, so var2 now is an alias for address 0x4002. And the way labels work is they basically just sort of, so the first, our var1 line starts at address 4000, initializes 2 bytes of memory. So we've now used up memory at address 4000, 4001. And then our next label basically starts at the next unused address in data memory. So var2 is an alias for address 4002. Now, the .word command initializes 16 bits of data memory at a time rather than 8 bits. So I should really have written if I want to write 33 to a 16-bit word, I can just say 33 and it'll automatically initialize the most significant byte to 0. But it's a little bit clearer if I just if I'm explicit about the fact that we're working with 16 bits. Now, this is how we so we can use .byte and .word to initialize data memory with numerical values. Sometimes we're also interested in working with ASCII characters, and we can use characters to initialize data memory as well. If we want to put some text, maybe we've got some UART communications or something like that we're implementing. And so I can create a label called string1. And if I wanted to, because each ASCII character is one byte, if I wanted to write the string dog into data memory, I can surround dog by these single quotes that will write the numerical ASCII value into data memory for dog. And I can finish that with the null character, because remember, all strings in C need to be terminated with a null character, which is equal to 0. In this case, str1 is an alias for address 4006, right? Because I think that's right. So if we look at our var2 line, 0033 was written at address 4002 and 4003 because it's a 16-bit word. Word 0044 was written at address 4 and 5. And so that means the next label we write down starts at address 4006. Now, it is also possible for us to, if we want to, if it's a little clunky to write out the individual characters to initialize a string, the assembler also does have an ASCII directive, which allows us to just initialize a regular old string in double quotes. And this will write dog in ascending bytes in memory. However, it isn't smart enough to automatically put in a null terminating character. So the way that you do that is you go \0, and that makes sure that it terminates with a 0. And just to switch back to the slides for a second to kind of consolidate that knowledge, remember that the data segment starts with the .data directive. Everything that follows .data is used to initialize values in data memory. The .global do copy data links in a bit of library code that actually copies the values in our data segment into data memory. We've then seen that in data memory we can use a series of what are known as labels. And remember, a label is just an alias for an address. So a label just represents a location in data memory. The very first label we put in data memory has address 4000, and then the addresses represented by the other labels depend on how much memory each label initializes. The syntax for labels is always just a string followed by a colon. And as we said in our example, var1 is an alias for address 4000, var2 is an alias for address 4002, and so on. We saw 3 ways to initialize data memory. The first one was using the .byte directive, which initializes 8 bits of memory to a value. You can initialize multiple bytes by having just a bunch of values separated by commas. .word initializes 16 bits of data memory with a value. Again, you can initialize multiple words by just having a bunch of values separated by commas. The .byte command can also be used to write ASCII characters into data memory, but really the .ascii directive is a little bit more efficient if you want to do something like that. And then you can just do double quotes right in your string and then make sure you terminate with the null character. So now that we've initialized data memory, now that we can see how we can sort of copy values into data memory, what do we do with them? Well, we already know, right? When we were designing our microarchitecture, we implemented load and store commands that allowed us to move data between the register file and actual data memory. And that's what we do with real assembly language on a real AVR chip. If you want to use a value in data memory, you've got to copy it into a register, do whatever you want to do with it. And if you want to store a value or if you want to store a value in data memory, you need to copy a register back into a particular data memory address. Now, we implemented load store commands using the X, Y, and Z register pairs. Those are still fully available to us if we want to use them. However, I'm going to introduce two new variants of the load and store commands that are just a little bit more efficient for us for the purposes of our discussion in these lectures. The first command is load direct from data space, or LDS, and the syntax for the LDS command is LDS, the register that we're copying data into, followed by an actual address in data memory. So LDS allows us to type the actual address onto the assembly language like command line, rather than having to indicate an X, Y, or Z register pair. Now, the nice thing about LDS is we can give it a numerical address if we want. We can say, copy in a value at register or at address 4000 into our register, but we can also use labels here. So we know labels are aliases for memory addresses. So rather than trying to keep track of all the numerical memory addresses, we can just give it the label that we want. And I'll show you how that works. The second command is store direct to data space, or STS. STS is the store version of LDS. So the command is STS, then we give it an address, and then we give it the name of the register that we're trying to copy to that particular address. And this address can be a numerical address or it can be a label. So let's switch back to the development environment. I'll put in some load and store commands, and then we're going to fire up the actual simulator and we're going to take a look at the data and instruction memory within the debugging environment of MPLAB-X. Okay, so the LDS and STS commands are commands that we are going to put into our text segment. So any kind of load, store commands, calculations, stuff like that, that's all going in the text segment. So the data segment is only used to initialize data memory values. You never put an actual assembly language command into the data segment. Now, there's a couple of things that we need to do with the text segment in order for our program to work. You'll know that when you write a C program, for example, your main function always has to be called main, right? If you don't have a main function, then your program won't run. That's always the function that's called first. The assembly language program, or our assembly language program, is basically the same. The region of our text segment that is run first has to also be named main. And there's two things that we need to do to enable this. The first thing we need to do is we need to type in another .global directive, and we say .global main. And this tells the assembler that we're going to create a program called main, and it's available to be linked to external library code. And basically that little sort of startup boot code that I was telling you about, that sort of initializes the chip and copies data memory and stuff like that, it's going to, when it's all done its initialization, look for an address in memory called main, and this just makes saying .global main makes that address visible to it. The last thing we need to do is we need to create a label in instruction memory called main. So labels can exist both in data memory and instruction memory, and they're exactly the same in both places. A label is just an alias for an address, in this case, main is an alias for an address in instruction memory and is the location where all of our assembly language commands are going to live. So .global main and then using the label main allows the initialization code to find our assembly language and then run it. So we're going to just do a couple of very simple commands here. I'm going to go LDS register 5 var 1, and this will copy a byte from address var 1, in other words, address 4000, into register 5. And that's all that it does. I could have also written R5 0x4000. It would have done the same thing. But labels are just a little bit easier because then we don't have to keep doing the address calculations in our head. I'm then going to use STS I'm going to type STS string to R5. This copies contents of R5 to address str1. And basically what's going to happen here is the contents of R5, which is going to be equal to 0x11, is going to get copied to the address represented by string 2, which starts at the character D. So we're going to see D get overwritten with address 0x11. But so this is our complete assembly language program. So now let's assemble it and run it inside our debugging environment so we can actually see what our data memory looks like as our program is run. So I'm going to save, then I'm going to go clean and build, and we're going to see we've built successfully. Now I'm going to, I mean, it's up to you how you like to set up your windows. I tend to like to set them up in columns. So there's a few things that I'm going to want to look at here while we're running. So I'm going to go up to the window menu, and I'm going to go down to target memory views, and I'm going to select program memory. And I'm going to try to move this up here. Yeah, exactly. So this looks kind of cool, right? So program memory, we see we've got some addresses, we've got opcode, and then we've got a disassembly column. So the disassembly column basically tells us the assembly language command that is located at a particular location in address or in instruction memory. So program memory is showing us instruction memory. This is address, whoops, let's see, I'll highlight this here. So address 0 is the first address in instruction memory. Opcode is basically the 16-bit binary machine language instruction that exists at address 0. And it's a jump command. And a jump command tells the program to jump to another address in instruction memory. A jump command is actually a 32-bit instruction rather than a 16-bit machine language instruction. That's why it takes up 2 lines. So jump actually occupies instruction memory at address 0 and address 1. And you can see the number 58 is actually contained inside the jump command. So this is telling us to jump to some assembly language code at address 58. And so if we go down to address 58, which is all the way down here, we see a bunch of more assembly language code and you're like, hey, I don't know what any of that means. I don't recognize any of that. This is basically all of that sort of initialization library code. So you didn't write any of this. This is just all of that library code that gets linked in order for the program to run. The way that we actually observe the code that we wrote is by setting a breakpoint. So if you go back to your source code here, you can set a breakpoint by clicking just over the line numbers, and then you'll create a little bit of a square there. And then if you go up to the debugger, the debug main project button, you hit that button, it's going to build again, and then it's going to stop at this LDS command. If we go back to program memory, now we can see that we're down here at address 84, LDS R5 address 4000. Hey, that's familiar. LDS R5 variable 1, but we know that var1 is an alias that represents address 4000. Another interesting thing that we can do here, in addition to sort of looking at our code, is we can look at the actual contents of data memory. So if we go to Window, Target Memory Views, we've got program memory. We can also look at SRAM data memory. And SRAM data memory starts at address 4000. And we can look at this and say, hey, here's a whole bunch of familiar values. So if we look at address 4000, we've got a value of 11 at address 4000, and then a value of 22 at address 4001. Again, as you're working through this, rather than trying to just sort of, just look at what's happening on my screen and just sit there and try to passively absorb all this, it's super important that you've got MPLAB open right now and that you are duplicating everything that I'm doing. So at this point, you should have MPLAB open. You should have a breakpoint created at the LDS command. You should have started the debugger, and you should be able to see SRAM data memory as well as program memory. Super important that you're following along within MPLAB rather than just kind of sitting there and just hoping that all of this sinks in, because it won't. This assembly language programming is not easy, and the only way to do it is to be like really hands-on with it. So anyway, we've got values 11 and 22, and that was copied in by this .byte command. We've then got values 33 and 44 that were copied in by the word command. And you'll notice you can see the zeros here too. It's written backwards because the address in the debugger just increases moving left to right. So the least significant byte is at address 4002. The most significant byte, which is all zeros, is at address 4003. 44 is at address 4004. 00 is at address 4005. And then at address 4006, 64 is the ASCII character for dog. The reason why we know this, you can see, this ASCII printout on the right-hand side is trying to show us that we've got capital D's and little d's. It doesn't do a particularly good job though. The best way, if you're interested in looking at ASCII character values, is to go down to this little format menu, switch it from hex to symbol, and then we get a much nicer picture of data memory. And it even shows us our labels. So var1 is at address 4000, and we've got value 1122. var2 is at address 4002, 330440. str1 is at address 4006, and we've got DOG and then 0, which is our null character. It shows up as a period, but it's you can go over here and verify that it's actually 0. And then str2, again, we've got DOG and our null character. So this is how you, when you're writing your assembly language code, this is how you can verify that you've initialized your data memory properly. Also, if you're manipulating values in data memory as your program executes, then you can see how data memory is going to change here. So I'm going to go back to just the hex format for data memory here in a second. And I'm going to add one more piece of information to our debugging screen. And that's going to allow us to see the value of register 5. So we can't use our data memory window to view the values in our register file because the 32 registers in our register file are not mapped into data memory space or instruction memory space. But we can still look at them by setting a watch. So if you go into the debug menu and if you select new watch, it's going to give you this little window here. If you click on SFRs, which stands for Special Function Registers, you can literally write in R5 as your the register you're interested in looking at. Hit OK, and then over here we're going to be able to see some watches. I'm going to organize my window a little bit differently here. Sure, let's do that. I had some other watches for other registers. I'm just going to delete that. So here's register 5, and right now it has a value of 0, but our debugger will stop. So if we set a breakpoint, it sets or it stops the program just before the breakpoint command is executed. And so if I go up here to my my debugging window, there's step over commands and step into commands. We want the step into because step over sometimes ignores certain functions related to, or assembly language commands related to function calls, which will be important later on. So we're going to use step into, and I'm going to just click it once. Over here, we can see that our little green arrow has progressed from LDS to STS, so we've jumped to the next command. If we look at the value for R5, we've changed from 0, 0 to 1, 1. So basically, our command has done what we expected. We've copied the value from address 4000 into register 5. Now, the last thing we're going to do and we can see down here in our instruction memory window, we've jumped ahead to STS 4010, which is the start address for string 2. We can tell that if we go back to our symbol readout here, str2 is next to address 400A, right? So that's why we've got 400A down here in our program memory area. And if I step one more, we're going to see the value at str2 change to 11. So that was the value contained in register R5, and we copied it into the location at str2. Okay. Now, down here, we've got jump to EEPROM end. This is basically the command that's thrown in here at the end of our program. So this is just going to jump to the end of the EEPROM, and then our little program's going to hang there. It's not going to do anything more. And this is basically all I wanted to show you. So you can see basically I've kind of taught you two things in this lecture. This is a pretty busy lecture, right? Because on one hand, we've talked about assembly language programming with memory, data memory, the different sort of address spaces within the AVR chip. We've sort of gone over that. We've talked about the data segment, the commands used to initialize values in data memory. We've talked about a new variant of the load and store commands that are a little bit more convenient to use than the XYZ ones that we introduced with our microarchitecture. And I've also introduced basically how to work in the debugging environment in MPLabX when using an assembly language program. Super, super important that you got this working by the end of this lecture. If you didn't, go back, go to the different steps, pause the video, make sure that you're sort of following along. If something's not working for you at home, post a question on the discussion board, ask, maybe there's something configured incorrectly. But all of my assembly language lectures, I'm basically going to be doing simultaneously on slides and in this development environment. And we're going to be looking at data memory locations. We're going to be looking at register values, and it's really going to be central to understanding how we're going to be using assembly language. When you start to do assembly language for the assignment, you can basically use this to check your work. And so it's really important that you don't just kind of let this blow past you. And it's not supposed to be easy, right? Like assembly language is, it's tricky, and it really gets us into sort of maximizing kind of the debugging capabilities that exist within a development environment like MPLabX. But it's good stuff, right? Like we're seeing all of the details. This is exactly what happens on a real AVR chip. We're simulating it, but if you used your pick kit to program an actual AVR device, this is exactly what would be going on that AVR device. And it's allowing us to sort of more fully enter into understanding how to use assembly language. And this will continue in the lectures that are coming up next.